Today we're going to be talking about the natural log. So we're going to evaluate expressions using the natural base and natural logarithm. And then we're going to do some exponential equations and inequalities with the logarithm and some real world examples on where we would use these. So the natural base is the function of e to the x, or for exponential growth, continuous exponential growth, or continuous exponential decay is e to the negative x. This would be used for half-lives and things like that in chemistry. This could be used for population growth and other things of that nature. But those are formulas that we do end up using. The inverse of a natural base exponential function, which are the e to the x, are considered a natural log. So it's log base e. Now, log base e is used quite a bit, specifically in calculus. And so we have an abbreviation for it. We call it the ln of x, the natural log, logo natural of x, if you so be it. But the ln of x is typically how that is said. So we want to go ahead and rewrite this as an equivalent equation. So e to the x equals 23. That's an exponential form. So how do we write it in logarithmic form? Remember, this is our base, and then we switch our two values. So we become log base e, and 23 equals x. Now log base e, again, we rewrite as just ln. So ln 23 equals x. And that is something we could go ahead and type into our calculator if we wanted to go ahead and get that value. Write this one in exponential form. So log base e, and then of x is going to equal 4. We have to switch those around. So x equals 4. So ln of x equals 4. So what about this one? Again, we're changing the 15 and x around. So it's the ln of 15 equals x. Excuse me. All right, and here we have the ln of x equals 4, because again, those get switched around. And we can go ahead and take this and write it in exponential if we want. So we can go ahead and go backwards. So again, this is going to be base e, so it's e to this power is going to equal x. And then here, e to the x is going to equal 25. So e to the power is going to equal x, or x is going to equal e to that power. And here, 47 is going to equal e to the x. We can even apply some of the properties that we've had before. So this 4, again, remember, is going to go up as an exponent. So that's 3 to the 4th, which is 81. And since it's plus 6, we're going to multiply that. So this 3, the 4 goes up there. And so we get 3 to the 4th times 6. So 81 times 6 is 486. And that would be our value. We could then, of course, type that into our calculator if we wanted to. We could have probably typed in the original one, but just showing that we can still use the properties that we learned before. Just a little bit of review. So this 2 is going to go up, and we got a bunch of pluses, so we're going to multiply all those things together. So it's 3 squared, and then 3 squared times 4 times y, which will give us 36y. So more combining, the 2 is going to get the 4th power, so 2 to the 4th times 3. 2 to the 4th is 16 times 3, which is 48. And here we're going to put the 3 to the 3rd, which is 27, times the 3rd would be 9 times x, so 9x. All right, so how do we actually use this? So there's a base called e. It is in your calculator. If you look at the ln button, which is underneath the log, there is an e to the x button. There's also an e next to above the divide sign, so you can use it in either spot. The one by the ln is if you want to take it to a power. The one by the divide is just an e if you need it for whatever value there. But most of the time we'll take it to some sort of power. So in order to solve something like this, we're going to have to get the e by itself, and then we can take the log of both sides, just like what we did yesterday. So we're going to have to move the 4 over and then divide by 3. Now, we could take the log just like what we did yesterday, but there's an advantage of taking the natural log, the ln. Because the ln and e are inverses from each other, they will cancel each other out, getting rid of this e value. So if I take the ln of both sides instead of just the log, these e's are going to cancel out. So I get negative 2x equals the ln of 2, and then I divide by negative 2, and I get my answer of negative 0.3466. Notice again, we're still using our 4 decimal points, but that's how it goes here. So again, I got to get my e by itself, and then if I take the ln of both sides, those will cancel, leaving me just that negative 2x here. ln of 2 we haven't done anything with yet, but we can type that in our calculator. ln of 2 divided by negative 2 does give us this value. All right, so trying another one here, we're going to have to move the 5 over and then divide by 2, and then take the ln of both sides, and you should get the negative 0.8047. All right, what about if we have an ln? Well, now we're going to have to do the e of both sides. So we got to get the ln by itself, so we're going to divide by 2. So ln of 5x equals 3. And now I take the e of both sides. And this ELN is going to cancel here, but this is going to be e to the third. Notice it does go in as an exponent. It's e to the x. Okay, so this 3 goes up as an exponent. So now 5x equals e to the third. And then you're just going to divide by 5. E to the third, again, you can use your calculator. So if you hit second ln, it comes up, and then you do 3. And you divide by 5. All right, this next one here, notice we have a squared here. It is a greater than, so we're going to still have that kind of a value that we have to deal with. So we go ahead and write it out, and then we take the e to both sides. Well, the e and the ln are going to cancel, and this is e to the 8th. Well, once we have the 3x plus 1 squared, we're going to take the square root of both sides, and we get e to the 4th. Then it's just a matter of subtracting 1 divided by 3 and typing it in our calculator, and we get 17.8661. And so we have a greater than symbol, 17.8661. One more here. I have that 3 on the outside. I got to divide it over, so I get 4. Then I go the e power here, and those cancel, giving me 6x equals e to the 4th. And then I divide by 6, and I get 9.0997. Here I have the ln. So I go e ln, and that's going to cancel, leaving me just the 4x minus 2, and we have e to the 7th over here. Add the 2 over and divide by 4, and we get 274.6583. You should have the 4 decimal points. I don't know why they did not here. All right, the continuous compound interest problems. They're also called PERT problems, P-E-R-T. Principal, rate, and time. And that will be what our amount is in the account afterwards, or for our population, or our half-life, or whatever it is. So suppose you deposit $7,700 into an account paying 3% interest, compounded continuously. What's the balance after 8 years? So the principal amount is $700. The rate, make sure when you write it in as a decimal, so 0.03 times 8. 0.03 times 8 is 0.24. So 700e times 2.24 gives us a value of 889.87. So after 8 years, that's how much will be in the account. How long will it take for the balance to reach 1,200? Well, we do the same kind of deal here, but this time we do not know the time. So all the other values are the same. We can really just make this an equal, that's fine. We're going to have to get the e by itself again. So we divide by 7, and we get 12 over 7. And then we can take the ln of both sides. So the ln and e will cancel, leaving me just the 0.03t. We're going to divide by 0.03, and 17, almost 18 years. Awful long time, huh? Suppose you deposit, how much would you have to deposit in order to reach a balance of 15 after 12? So we don't know what the principal is this time. We want to know what that principal is because this is the amount we want at the end. So we're still going to go ahead and get p by itself, so we have to divide by this. And again, that's just entering into the calculator. And so you need to have $1,046.51 in order to get to that value that you wanted. And that's what I have for you today.